3.6, stoichiometry. Oh, my favorite, one of my favorite topics. I can't say my favorite, but it's in definitely the top 3. Stoichiometry. First, let's look at the learning objectives that AP expects us to master. In Unit 4.5, when we watch the AP Daily, when you're doing stoichiometry, you have to use a balance equation and quantitative information. Grams, moles, molecules. But in order to do Stoic, the true definition is a balance equation. What we've been doing, those are just called conversions, okay? So nothing in the beginning of Chapter 3 has been technically classified as stoichiometry. So now we're going to use a balance equation to get from one side to the other. So take a minute, ladies and gentlemen, to read and annotate what does AP expect you to master. And let's start with the topic called mole ratio. Mole ratio is the only way to convert from reactants and products in any type of balance equation. You cannot use grams. Cannot, because everything has to go through moles. So when you're going from grams to grams, it doesn't take into account the coefficients in a balance equation. Because remember, coefficients are moles. So in order to use mole ratio, we have to have a balanced equation. So if I had grams of A and I wanted to go grams to B, I know this chart looks very familiar to you. I would go from mass A to mole A, and I need molar mass, which means I need the periodic table. If I want to get to a new chemical, because if I had a reaction A makes B, then I need mole ratio, and this is when we look at our balanced equation. In my balanced equation, the coefficients are the moles. So I just need to look at the balance equation and only at that point. So then once I cross the rainbow to get to mole B, I'm going to go back up to mass and I need the periodic table again. I'm not saying that's the only type of calculations we're going to do, grams and moles. I could be doing particles, which means I need Avogadro. Same thing on this side. I could say I want atoms or ions, which as we've done in 3.4 and 5, you count what you see, okay? We're going to get to the volume part, this part right here. This is going to be in Chapter 10, okay? But other than that, you have about 80% of this chart mastered. So let's do some samples, and let's get our calculators going, okay? All right, so I see an equation, and you always want to check if it's balanced, which I'm looking at those chlorines, and those definitely are not balanced. So I'm going to do a quick little balancing. I have, let's list our aluminums, 1 on each side, hydrogen, 1 and 2, and chlorine, I have 1 and 3. So I could maybe think about a diatomic or do think of a fraction because I do see a diatomic, but we got to balance those chlorines first. So I have 3 chlorines versus 1, so I do need a 3. And I could put a 3/2 if I wanted to there. If I want to keep the whole numbers going, so instead you would have a 2, a 6, a 2, and a 3 if you did it with whole numbers instead. The reason why I'm showing you the whole numbers is because when you do stoichiometry, you really don't want to deal with the fraction, but I'm going to show you both ways. So calculation number 1, I have aluminum and HCl that reacts together. If I start with 0.36 moles of AlCl3 is produced, how many moles of H2 are also produced? Well, I'm changing the chemical and I need a balanced equation. This is not like going from like CO2 and I just want to get to carbon. I don't need a balanced equation. I can just count what I see. I'm changing the chemical completely from one element to a different element. So according to our stoichiometry, let me have my little color picture up here. I got moles, so I'm starting right there at mole A, and I just want to get to moles of a different chemical. Mole A to mole B, one step. So I just need a balanced equation. So 0.36 moles of AlCl3. The purpose is not to get rid of the mole. The purpose is to get rid of the chemical. So according to my equation, and I'm going to use the whole numbers, okay, whole numbers right up here. My AlCl3, I see a 2. And for hydrogen, I see a 3. Okay? Bye-bye. AlCl3, I'm going to multiply by 3 by 0.36, divide by 2. And we don't look at 3 and 2. These moles, these are not sig figs. Okay? So I'm basing my sig figs off of that starting value only. So it looks like 2 sig figs, so 0.54 moles of H2. We're going to highlight that answer. Now, I'm going to do it in black, so that way you see where I got if I did it the fraction way. So because right here there's a coefficient of 1, I could put a 1 down here instead. But then my hydrogen, I would have to put 3/2 on top. Nothing wrong with that. That's a fraction. I'm still taking 0.36 multiplied by 3, divide by 2. I'm still doing the same thing. It's just students aren't very comfortable sometimes with using fractions. So I want to show you both ways because I'm cool with either way. Let's keep the same equation going, but now how many grams of aluminum are required to produce H2? Now, I'm going to use whole numbers instead, the numbers that are in red up there. But I have H2 that I produce. How much do I need of aluminum to make this reaction go? So 75 grams of H2. And according to our chart, I'm going to start with grams of hydrogen, go to moles, cross using the balance equation, and then go back to moles. So I'm looking at 3 steps here. I always like to figure out how many steps I'm going to have first so I can have my map going. So grams of H2, and there's 1 mole. Now, that's a diatomic. I don't need to see molar mass of a diatomic. I just need to make sure 2 times 1.008. I just need to make sure I keep the appropriate sig figs, so 0.016. Okay, bye-bye grams. Now here is where the balanced equation comes in. Let's get rid of H2 and get to the aluminum that we want. So according to my balanced equation, let me scroll back up. Like I said, I'm going to use the whole numbers. My H2 is a 3, and my aluminum is a 2. So the purpose is I got rid of the chemical. And now my last step, remember 1 mole is always the molar mass of aluminum. So I'm going to need some assistance with my periodic table. Aluminum is 26.98 and bye-bye mole. So I'm just going to highlight 75 times 2 times 26, and then we're going to divide by 2, divide by 3. And if we do this correctly, we should get that answer. And the reason why it's 2 sig figs is because what my sig figs are based off of that 75, those circled numbers, they have 4 sig figs, but 75 has 2. So I'm going to keep those 2 sig figs, number, unit, chemical. Okay? Let's try another one. This time, what if you, oh, and bad spelling of chlorine. That's bad. Sodium and chlorine gas. All right, so sodium is a solid. Chlorine is not only a gas, but it's a diatomic. Naturally doesn't occur by itself. So I got to put Cl2. Sodium, when it comes together, is +1. Chlorine, -1. That 2 doesn't come over. You got to use that to balance. So sodium +1, chlorine -1. Okay, doesn't matter what it forms. It's probably going to be a solid. Okay, sodium chloride. But I do got to balance it. Now, because I'm going to try to stay away from the fraction, you could put a 1/2 right there in front. But because I'm doing math, I like to keep whole numbers when I'm doing stoichiometry. So, number 4. How many grams of sodium chloride, so that's what I know I need to solve for, can be formed theoretically? So the last video, we're going to talk about theoretical versus actual. Theoretical, which means you have 0 error in the lab. 0 errors. You were perfect from beginning to end. All that can be produced is what was given in a combination reaction in which 30 grams of chlorine react with excess sodium. Now, the excess sodium, going to make a little bit more sense in this last video, 3.7. That means that excess sodium, not all of the sodium was used that they gave you. That means chlorine is what's called your limiting. He ran out first. And because he ran out first, he dictates how much you're going to form. So I'm going to start with that 30 grams of chlorine. And I want to know theoretically how many grams of sodium chloride am I supposed to produce. Okay? I like to write the numbers under the balance equation so I can keep track of my thought process where I'm going. Grams of one chemical, grams of somebody else. Looks like I'm doing 3 steps. 30 grams of chlorine. Now that's a diatomic, so I need to take chlorine's molar mass, which is 35.45, and I need to multiply by 2. Now remember I said with diatomics, I don't need to see, but here's the beware. 35.45 has 2 after the decimals, and times 2, you got to keep the 2 after the decimal, and that's going to be 1 mole of chlorine. So bye-bye grams. Now let's look at our balance equation. I have 1 mole of chlorine, and because I want the product, I have 2 moles of salt. Bye-bye Cl2. And now I do need the molar mass for salt. Luckily, they're both 1 to 1, so I just need to show a quick little calculation. Sodium, 22.99 in grams. Chlorine, as we said, 35.45. So when we add that up, 58.44 grams of sodium chloride. And molar mass always equals 1 mole. So bye-bye mole. Oops, that mole. So I'm going to highlight for you. We're going to take the 30 times the 2 times the 58, and we are going to divide by 70.90. And if we work this right in our calculator, because always check my calculations, we had 4 sig figs everywhere except that 2, so 40.46 grams of NaCl. So now the question is, what does this mean? Okay, if you start with 30 grams of Cl2, theoretically, we like to call this theoretical yield, the maximum amount that you can produce is 40.46 grams of that salt in this reaction. But remember I said theoretically, if you had 0 errors, no solid fell out of the crucible, you heated it to completion, okay, you did everything correct, somebody didn't break a test tube. So there's always going to be error, ladies and gentlemen. You're just trying to minimize the error. Okay. Another type of way of using stoichiometry is using density. Okay. How many mils of bromine are needed to react completely with 40.0 grams of calcium iodide? Well, I need a balance equation. Okay. So before I even tackle the math, how many liters of bromine react with calcium iodide? All right, so let's get a balance equation. What do we know about bromine? Well, bromine not only is a liquid, but it's diatomic. Calcium iodide is ionic. So calcium's plus 2. I see IDE, so that means it's iodine. So I'm going to say CaI2. Okay? Didn't tell me state of matter, but I do know it's a solid. Okay? And what it's going to form is this is a type of reaction called single replacement, which you're going to learn in chapter 4. And the bromine, what happens is it replaces the iodine and gives you Ca, which is plus 2. Bromine is negative 1. So if this is a plus 2 minus 1, it's just a coincidence that that 2 on bromine is going to be also right there on bromine. And that's going to be a solid. And then what am I going to form? Well, remember, they just swap places. iodine naturally is a solid. But what do I also know about iodine? It's a diatomic. Conveniently enough, my equation is also balanced. So that calcium plus 2, the bromine's -1, so I got a crisscross, and that's why that 2 is on the bromine. So my balance equation looks good. So I'm going to start with 40 grams of that calcium iodide. Okay. Now, why do I want you to think of density? Well, the density of liquid bromine, 3.12, I'm going to use that eventually. Well, let's get rid of the calcium iodide, which calcium iodide they said was 40 grams. I want to get to this guy, but I want liters. So I have to get to a new chemical, which means I need stoichiometry. So 40.0 grams of calcium iodide. Well, we need some molar mass. Calcium, there's only one of them. Calcium is 40.08. Iodine, big molar mass. I need to take 126.9 times 2. So iodine, 253.80. Always keep the 2 after the decimal. So we're going to add that up. And I'm going to get 293.88 grams of that calcium iodide. So I'm going to put that on the bottom. And what goes on top? I need moles. Okay, so bye-bye grams. Now we get rid of the chemical. 1 mole of calcium iodide. And on top, I'm trying to get to bromine. 1 mole of Br2. Okay? And I'm going to, oops, sorry, not equal sign. I want to get to grams. Now, the reason why I want to get to grams, because look at density is grams per liters. Let's see where you see where I'm going. So when 1 mole of Br2, well, bromine on the periodic table is 70.9, but I don't have just bromine. I have diatomic bromine. So 70.9 times 2, 159.80. Oops, Br2. So bye-bye moles, bye-bye calcium. And when we plug this in, 400 times 159 divide 293, I'm going to get 217.5 grams. So if life was perfect and I started with 40 grams, this is what we like to call, theoretically, that is all I can produce. Now, let's remember density. Density is mass over volume. Remember our cool triangle? DMV. Okay? I have mass of bromine. So I have this guy. Okay? I have the 217.5 grams. And I told you the density of liquid bromine is 3.12 grams per mils. I want liters. Well, that's volume. I want this guy. Oops, I don't mean to put my little line right there. I want volume. So what's the equation to solve for volume? Well, volume is mass over density. Okay? If you need your triangle, use your triangle. But that doesn't count as an equation. You got to tell AP either density or you got to tell them this equation. But you got to give them at least one, but use your triangle to help you. What's the equation? So mass, 217.5 grams. The density, 3.12 grams per mils. Look at the units. Grams divided by grams are gone. And what is 1 over mils? Well, that's called a reciprocal. And there's mils. Okay, we're not done yet. So let's plug this in. 217.5 divide 312. And I'm going to get, looks like 3 sig figs. I'm going to get 69.7. And this is bromine. But now here comes liters. Hey, is there anything I've ever taught you to go from mils to liters? Oh, I think we need a little King Henry in our life. So remember liters. And then we have deci, centa, and milli. So because I have milliliters, I need to go 1, 2, 3 to the left. So 1, 2, 3, put a 0 right there. So my final answer, 0.0697 liters of bromine. Okay? All right, that's how density can get played in here too. Let's try another one with density also, okay? Because density, it takes us a little time. I have mercury, and it's added to silver nitrate. So it looks like I'm going to need a balanced equation. So mercury, Hg, we know it's liquid, it's not diatomic, and it reacts with silver +1, nitrate -1, but that's a polyatomic. So I'm going to have AgNO3, and I do know that is aqueous. And it says, how many grams of mercury nitrate will I form? Well, I already know one of the products. Okay, so this is another one that's called single replacement. That mercury is going to swap places with that silver. So I'm going to get silver left over. And we know silver is a solid. And it already told me what one of the other products is going to be. Hg2NO3, parentheses 2. And most of the time, mercury, when it forms stuff, will be a solid. Doesn't matter the state of matter right now. They would have to tell you. All right, this guy is definitely not balanced. So let's count this up. So I got mercury. I got 1 versus 2. I got silver, 1 on each side. I got nitrogen, 1 versus 2. And oxygen, 3 versus 3 times 2 is 6. Well, let's fix the mercury first. Maybe that'll help. So I'm going to put a 2 there. And now we just need to fix the nitrogen and oxygen. So it looks like I need some assistance on this reactant. So I'm going to put a 2 here, which means now silver is 2, nitrogen is 2, and oxygen is 6. And it looks like I just need to help out my silver. So I'm going to put a 2 in front of that Ag, and we should be good to go. All right, so what do I have? I have 46.7 mils, so I'm going to put that information under here. This is another way of doing like a know and a don't know. I find this more helpful than doing a chart. Excess silver nitrate, so if this guy was excess, that means mercury ran out first. That's your limiting. And we'll get more into that the next video. How many grams of this product, so that's what I'm solving for, could theoretically be produced? Well, if I got mils, I hope AP tells me something about density, okay? And if we do this right, we should get around 800 grams. So let's look at density, our cool triangle. D and V. This time I have the density, and this time I have the volume. Well, let's find mass. Okay, so now I tell AP mass is density times volume. So density 13.6 grams per mils, and this is of mercury. And we're going to multiply that by volume. And because it's mils, if you don't want to draw an X, you can make it look like parentheses instead. Because that way you can see what's going to happen with the units. 46.7 mils. So by mils. And 13.6 multiplied by 46.7. And looks like 3 sig figs, we're going to get 635 grams of mercury. Now let's see where you think where we're going. I got grams of mercury, and I want to go grams of this product. Grams to grams, well, that's 3 steps. So 635 grams of mercury. And I'm going to set you up with your 3 steps, but you're going to finish it off. And if we do this right, like I said, we should get that answer in blue. So we're going to go grams of mercury. And there's 1 mole in mercury. We're going to look at our balanced equation here. And I see 2 moles of mercury, and I only see 1 mole of that product. So 2 moles of mercury and 1 mole of that product. And because we want grams, we need molar mass. And because I know you enjoy so much solving for molar mass, I'm going to let you continue. So in the end, ladies and gentlemen, we should get 831. And I'll see you on the next video.